We are going to start the last lecture of this workshop. The speaker is Karin Sandstrom from US. She's gonna tell us about the low metallicity industrial medium. So we will have a short break, about 1 hour later or so, and more discussion time after the talk. Please take it over.
All right. Can everybody hear me okay? Well, welcome to the last lecture. You've made it. Are you excited? Excellent. So my name's Karin Sandstrom. I'm a professor at UC San Diego, and I want to take this moment to just remind you again that we now have an astronomy and astrophysics department. So if you were ever looking, for instance, to become a postdoctoral fellow somewhere in the US, if you want to study the ISM, especially low metallicity ISM, or FANGs or something like that, got a really nice spot for you at UCSD. So please get in touch. And if you're looking eventually for jobs, we will be hiring new faculty as well, starting soon. So with that, let's get on to the low metallicity interstellar medium. So who here works on questions related to the low metallicity ISM in their research? Okay, so good chunk. So many of you will be familiar with a lot of this material. And the other thing that's cool is, particularly at this workshop or this school, many of the experts are here. So if there's a bunch of you in the audience whose plots are going to come up here, and I may be like turning the mic over to you to explain something if there's any tough questions. So just keep your eye out. Okay, so to get started, I'm gonna try to make this thing click forward. Here's a little overview of what I want to cover. So I want to start first off with just talking about what is metallicity and when do we consider it low? And there is no definitive answer for that. And I will actually be interested to hear all of your perspectives on what you consider low metallicity. We'll then briefly talk about where we find low metallicity conditions. And then I'm going to talk about dust, because dust is greatly affected by changes in metallicity. It is metals, so that makes sense. After dust, we're going to pause for a bit, and then we'll go on to talk about some of the effects that low metallicity has on the interstellar medium, just going through ionized atomic and molecular phases. And then we will end with some future perspectives. A little spoiler alert. We now have an incredibly powerful telescope that can study the conditions in low metallicity galaxies at redshifts that you wouldn't have even believed like 2 years ago. So the low metallicity interstellar medium is now a topic of great interest for everybody. Okay, so we'll start with what is metallicity. And at the beginning, I want to show this beautiful plot based on Chiaki's work, showing you the periodic table, all of the elements, and in each little box is a kind of cartoon diagram of their evolution over time. So from what sources these come, whether they're made in the Big Bang, exploding massive stars, various other sources. And so metallicity for us is everything other than hydrogen and helium. But we can narrow it down a little bit more for what's relevant for the ISM, because, despite how interesting something like, I don't know, pick a random thing here, might be, it's probably not a big enough contribution by mass to matter. So the things that really matter for making dust, or contributing to ISM processes, except in kind of weird edge cases that occasionally happen, are elements where you have something that's got a mass contribution relative to hydrogen of greater than about 10 to the minus 4. And you can see what those are shown up here. So we have the things we're all very familiar with: carbon, nitrogen, oxygen. We have some noble gases. We have iron and nickel. So if you know back from some of the talks we've covered in this course already, many of these things are the components that go into making interstellar dust. magnesium, silicon, iron, oxygen, carbon. So the reason we care particularly about these is because of their mass contribution. So just a bit of notation. We describe the fraction of various elements in a couple of ways. One of them is using this X, Y, and Z notation. So this is the abundance of hydrogen, helium, and metals, everything other than hydrogen and helium. So Z is the metal mass over the total baryonic mass. When we talk about this in terms of number, we often use notation where you have some element relative to another in these brackets. And this implies the kind of notation here where we're doing the log of a ratio and comparing it, in fact, to some reference abundance, which is often solar abundances. In another set, and we're going to use these a lot for ISM gas phase metallicities, we will use this notation of 12 plus log X over H. And so this is handy because when we look at the list of the number abundance by number of elements, if you add 12 to it, you're rarely dealing with negative numbers. So this was handy at some point. And you will see that in these notations, the one that'll come up most frequently is oxygen. And this is going to have a value in 12 plus log over H of something like 8, around 8. Higher than 8 for solar. And then we're going to talk about some galaxies that are lower. And just to note, in case you haven't thought about this, you might be confused as to why some people, when they talk about metallicities, use a different notation and often rely heavily on iron if they're thinking about stars, versus ISM people who are often thinking about gas phase metallicities and talk mostly about oxygen. And in a lot of cases, they'll just default to whatever that language is and maybe not ever have explained why. It is because it's very easy to see iron lines in the spectrum of stars and measure the metallicity from those. So iron becomes kind of the default thing for stellar metallicities in some historical sense. And as you'll see in a few slides, for ISM metallicities, which we often measure using H2 region spectra, oxygen is whoppingly bright. And so oxygen is the easiest thing to measure. And so our initial, thinking about metallicities often centered on what oxygen was doing. So in general, we also need a reference point, and the sun is the most natural of those reference points, obviously. It's the thing where we really can measure the metallicity as best possible using techniques that you can't do anywhere else, such as like astroseismology or helioseismology, that lets us tell, based on the density of various layers of the sun, what elemental compositions are. So this is one of the key references then for solar metallicity from Asplund in 2009, the review article. And you can see here these abundance numbers. This is for the photosphere, and then a comparison for what's in meteorites, and they are slightly different because the sun has been sitting around evolving for 4.5 billion years and has altered a few of its elemental abundances. And you can see here a couple of the key sets of elements that we'll talk about. So the CNO elements, alpha elements, and then iron peak. So the interesting thing for the ISM, though, is that if we're trying to have like a reference abundance for the ISM, especially just like the ISM around us in the Milky Way, it probably shouldn't be the sun. The sun is 4.5 billion years old. It wasn't, the gas that we are sitting in has nothing to do with the gas that the sun was formed from. So potentially better abundance reference for ISM purposes is if you can go out and look at young stars, like B stars, and measure their abundance patterns. And that is what was done in this paper. So what you see in this plot is the value for the solar photosphere, the value for what people think the kind of protosolar nebula was. So this was initial conditions of the gas that formed the sun. And then this histogram is a distribution of a bunch of young stars that have had their abundances measured in this paper. And stars are really nice for this because there's no dust in the stars. I mean, that's not always true, right? like really low mass stars or something sometimes have weird things in their atmospheres, but hot stars, no dust. Everything is gas. So you have access to measuring all of these elemental abundances. And you can see here that there are slight differences in some of these, and in particular, a few that are quite big contributions to the ISM by mass, carbon, oxygen. There is small offsets between what we see in B stars in the solar neighborhood and the sun's abundances. So this is good to keep in mind, and you can see here a comparison between this, the X, Y, and Z values you get for this work versus the sun. Cool. So just on that note, since we're going to be talking about some of the lowest metallicity galaxies occasionally, one interesting thing is that the helium abundance changes as a function of time because of the processing that occurs in stars. And this is a plot showing oxygen, which we can easily measure from in the gas phase, or not easily, but at least measure in the gas phase for galaxies using H2 region spectra, and then helium abundance. And this point here is actually one of the lowest metallicity dwarf galaxies known in the local universe. And you can see that to within its error bars, it's pretty close to the primordial helium abundance. So what was made just as in the process of the Big Bang. Cool. And you can also see that the helium abundance changes systematically with O over H, as you would expect, because this is the enrichment by many generations of stars forming. Okay, so I want to talk briefly about how we trace ISM metallicity. There are a few options. So in theory, you could go out and measure the absorption lines that come from various elements that are in the gas and calculate how much there are of each relative to hydrogen. And this is great because it lets us detect metals in gas that's cool. For instance, the neutral molecular gas. We don't have to have it heated up a ton to, reveal elements for us. However, in this situation, in the Milky Way, and certainly in lots of galaxies, most of the heavy elements will be in dust. A lot of the heavy elements, in some cases, almost all of them, like iron. So this is not ideal from that perspective, but there is still a lot to be learned using the abundances from absorption line studies. The other way we can try to approach this is we can go to places where gas is quite hot, where it's been photoionized, for instance, and there the electron collisions with electrons will excite the energy levels of various ions and will have these emission lines that we can interpret relative to the emission from hydrogen. So this is great. Here, we understand, hopefully, if we can measure something about the temperature, how they're being excited. There's less dust depletion to worry about, though not none. So just keep that in mind. And but there are some downsides as well. So if we want really accurate metallicities this way, we really should know something about the electron temperature, which isn't super easy sometimes. And there are some still tiny bits of depletion that we probably have to worry about in interpreting these measurements. Great. So then lastly, we've already talked about this a bit. If we have stellar spectra, if they're young stars, they should be a good representative of the gas they formed out of. They haven't changed things much. And you can learn about their abundances, but we can't really do this in many other galaxies. We have to resolve individual young stars, and that is something that you can only do really in the local group and very nearby. Sorry, I am gonna probably have to cough a bit during this talk. I was sick earlier. Okay. So I want to go back to the measurement of abundances in cold gas and the depletion, or the fraction of the elements that are not in gas, but instead in dust. We call those depleted. And here's a little illustration of this. So what you have here is the abundance of a bunch of different elements relative to solar abundances towards a particular star in the galaxy that's got quite a bit of gas and dust in front of it. And what you see is the abundances you expect, and then the abundances that you measure. And what you see is that for a lot of elements, especially those that have these high condensation temperatures, so these are refractory elements, so-called, they are highly depleted. So they are far less abundant than you would expect based on the solar abundances. So this actually shows us directly what's in dust. We're going to come back to that. Here's a, sorry, I need to take another. Ooh, that's bad. Okay. So I want to have a look at how we trace ISM metallicities. So this, we talked about going to places where the gas is quite hot, where it collisionally excites these lines from various ions. And you can see that here in the spectrum of an H2 region from the chaos survey. And what's nice about this, I think, is you can really tell which things are very bright, these collisionally excited lines, because we have this axis where you have to zoom in to see all these other tiny lines, but then there are these features that are whoppingly bright. So among the brightest of those lines are the oxygen transitions at 5007, 4959 angstroms. You can see those here. There's also O2, and there's nitrogen 2, and a few other lines from ions like sulfur. And in these places, if we can model the electron temperature and understand the excitation of these lines, we can measure metallicities. So here are some of those strong lines that are very easy to detect. So these correspond to relatively low-lying levels in the atom that are easy to excite at H2 region temperatures. Because they're easy to excite, it's actually hard to learn from those lines anything about the electron temperature at all. So we have to bring in other information if we want to know something about the actual temperature. But the behavior of these strong lines is actually correlated really well with metallicity. So here is a plot showing the sum of oxygen 3 and oxygen 2 relative to H beta as a function of metallicity. And this compiles a bunch of different strongline calibrations. So you can see at low metallicity, we have this increasing trend of these line ratios with metallicity. Then there's actually a turnover where things swoop back around. So if you are able to know which of these branches you're in, if you have some other information, you can use the R23 type variables to understand what kind of metallicity gas you're looking at. So this behavior happens because we have increasing oxygen abundance, so that's making the oxygen lines brighter. But at higher metallicities, the H2 regions get cooler and lower ionization. So that turns back around. So this is very handy, but there's obviously some issues in this process. So if we really want an accurate metallicity, it's much easier, well, it's not easy, sorry, it's much better to have something about the auroral line, or the higher excitation line within the atom. So here's one, for instance, for the O3 ion, and you can see it over here. So if we can measure that relative to the strong line, we have a very good diagnostic of the temperature. And then we can get what we call a direct metallicity measurement. And this is far less uncertain than what you get out of strong lines generally. Okay, so if we put all the information together, we learn about the population of galaxies from their strongline metallicities. What you see is something like this. So here we have the stellar mass of the galaxy versus its metallicity. And this is done using the Sloan Digital Sky Survey spectroscopy. And there's a very strong correlation between the mass of a galaxy and its gas phase oxygen metallicity, judged by these strongline calibrations. However, there is also a well-known issue with those calibrations. And in fact, if you use different calibrations, you can get quite different answers. So this is the range of systematic uncertainties from strongline calibrations. So the moral of this story is that we have a lot to learn still about strongline calibrations. And if possible, direct metallicities are often a more accurate way to judge the actual metallicity of the gas. So this is a plot showing a new version of that mass metallicity relationship where they have attempted to tie the strongline calibration to what's known from direct electron temperature measurements. And I just want to, we'll come back to this when we're talking about where we find low metallicity environments. But the point here is that as you get to more massive galaxies, they are more chemically enriched. There's a steeper slope for low metallicity galaxies, and then a turnover up here that saturates kind of at some slightly higher than solar potentially metallicity. And the behavior in this plot may be due to the fact that low mass galaxies just have had fewer generations of chemical enrichment, and that they are worse at holding on to the elements that they produce. They have lower gravitational potentials, and they can expel potentially more of the metals they make in winds. So before moving on, I just want to point out a couple of last things about metallicity. So we will often talk with just oxygen, but and that kind of intrinsically assumes that there's some overall scaling of everything with oxygen, and that's not actually true. So here is a plot showing a few elements where it works pretty well. So this is a compilation of measurements from Berg et al. 2019. You see neon, argon, nitrogen, and sulfur. And for many of these, you know, compared to higher metallicity galaxies, these dwarfs have similar abundance patterns. But that's not always the case. And in particular, nitrogen, you can see here, maybe a little bit of a spoiler from the trend that's fit, but there is a abundance pattern variation as a function of metallicity that's due to the primary and secondary production of nitrogen. So primary means it was generated in stars without relation to any previous chemical enrichment. So you would make that amount of nitrogen, that yield of nitrogen, regardless of what the metallicity is. Secondary production will depend on having some elemental enrichment already in these stellar yields. So just to note that if, you know, maybe we're not super worried about, you know, argon or something like that, but there's evidence that carbon relative to oxygen actually has quite a big abundance variation. So you can see that here. So this is the carbon to oxygen ratio as a function of oxygen abundance, and there's various fits here. But you can see that if we went to something, you know, around solar and then went to something around the SMC, which is maybe like 8.1, there's actually a not insubstantial change in the relative amounts of carbon and oxygen. So this is something that is important to keep track of. And interestingly, carbon to nitrogen doesn't have as much of a trend. So this is suggesting that maybe carbon also follows this kind of production pattern that we're seeing that nitrogen does. And of course, there are experts in the audience about abundance patterns. So at the break, we should have any other feedback on this particular topic. All right. So with that, now we know a lot about metallicity. What is low metallicity? So there's no strict definition here, and you know, you come up with a variety of ways to set this up. So it could be some factor lower than the Milky Way solar neighborhood, or we could pick a metallicity where the ISM seems to begin to change quite dramatically, and we will see something like that. So around 12 plus log over H around 8, things seem to get kind of weird. But I'm interested in anyone have their own low metallicity definition they want to share? No? All right, well, maybe we'll come back to that later. Okay, so I want to talk next about where we find low metallicity conditions. And there are a few likely spots. So first we have dwarf galaxies. And we're going to go through these in a little more detail, each of them. So for galaxies with less than about 10 to the 9 solar masses, due to the mass metallicity relationship, you tend to see low metallicity in those objects. The other thing is that more massive galaxies tend to have radially varying metallicity gradients. And that means that when you get to the outskirts of a disk of a more massive galaxy, you can get down to quite low metallicities. So the outskirts of galaxy disks is another spot. And lastly, high redshift galaxies. And this is because they just haven't had as many generations of chemical enrichment yet, especially when we're looking at things at redshift of like 8 or 10 now. So those are very early on in their history of enrichment. So here we've seen this already. We're gonna have a definition of dwarfs as about lower than about 10 to the 9 solar masses. So this means that something like the LMC, basically there's some boundary like LMC M33 like where you switch from what we would consider more massive galaxies to dwarfs. And so you can keep that in your head if you're familiar with those as kind of the transition point as to where things are dwarfs. One other point that's important here is that because they are small and turbulent and they can easily mix things together throughout their ISM, people argue that dwarf galaxies should be quite chemically homogeneous. I tried to find the killer plot to put in here to like demonstrate that point because I thought that would be cool. And, I was a little like, I don't know, I didn't really find the killer plot for that. So I just want to say, I think there's a spot here where we have a beautiful IFU on lots of different telescopes now, and we could point it at a bunch of dwarf galaxies, measure some actually electron temperature dependent metallicities, and really put a lid on that. So I think there are a few cases, the things that people publish seem to be like, oh, I found a dwarf galaxy that's not quite homogeneous. So the degree to which it is not quite homogeneous, I think, is something that we still need to quantify. So this is an interesting topic. I did want to point out, if you go to the lowest mass galaxies and the lowest heavy element abundances you can find, and these are often called extremely metal poor galaxies or XMPs, they actually tend to break the common relationships between like stellar mass or galaxy luminosity and metallicity. So you can see that here. There's a compilation of these galaxies from various samples, and including a few that are more commonly known. So Leo P, this is that one I mentioned earlier, one of the lowest metallicity galaxies known. So these apparently, when you look in detail, have a ton of recent star formation. They often seem to be interacting. They may have recent inflows of pristine material. So this may take them and move them kind of off of the standard relationships between mass and metallicity, for instance. So some of these are really cool because they're quite nearby and very low metallicity, and studying those in detail. Cool. So here's a compilation from the MANGA survey of radial gradient slopes for metallicity gradients in galaxies. And this is meant to show you that if we use these gradients, we can actually get down to relatively low metallicities in the outskirts of some galaxies. So this is a stack. So it shows kind of the median for each of these ranges of mass. And you can see the average behavior of the gradient itself as a function of stellar mass. So in general, right, you have a few decs per kind of effective radius, or a few tenths of a dex per effective radius. But there are occasionally galaxies that really stand out in this regard. And one of them, hopefully everyone's favorite, is M101. This is a real weird galaxy. We study it a lot because it's beautiful and face on and nearby, but it has a radial metallicity gradient that spans an order of magnitude. So it goes from higher than solar metallicity in its center to less than SMC metallicity in its outskirts. So it also has a very large disk. So this is a kind of a strange galaxy. And it becomes the kind of focal point for a lot of work. And sometimes I worry that it is a really weird one, so we should keep that in mind. But it is a really handy place to look at low metallicity because you actually get to control for a lot of the other aspects of, the galaxy's evolution, the distance, the resolution you're working at, various things by just looking at one galaxy. And I don't actually want us to roll down the shades, but when you look at these slides later, this is an image from Spitzer that shows PA emission relative to hot dust, so 8 to 24 micron ratios. And you can see this change from kind of green in the center to red on the outside. And that is also the metallicity dependent deficit of PAs. So you can just immediately see that in this galaxy. So just to point out, if we actually wanted to go to the very closest low metallicity environment, the outer disk of the Milky Way may actually be the best option. So the Milky Way also has a radial metallicity gradient. And this is a recent paper that was refining this using a couple of different metallicity updates and using Gaia-based parallax distances to the various H2 regions that are in this gradient calculation. So you can see that if we get out to 16 kiloparsecs in the Milky Way, we are down at quite low metallicities. So that is a interesting location to try to study things because it's really close. Okay, so I'm going to move on then to high redshift galaxies. And the key point for high redshift galaxies, right, is that they just have not had the time to produce as many generations of stars and have often on average and hold on to those elements over the course of their evolution. So if we look back at the history of star formation in the universe, peak is around redshift of 2. And this is a compilation of different metallicity measurements, some of them appropriate for like the intergalactic medium, some of them for galaxies. And if we look at redshift of 2, the damped Lyman alpha systems, which we've talked quite a bit about, which are probably some combination of outer disks of galaxies or some kind of streams occasionally or various other galaxy-related gas, you can see that the metallicity is quite low, so less than 1/10 of the solar metallicity. And we can look in this in a little more detail. So this is a compilation of mass metallicity relationships from simulations and actually observations of high redshift galaxies. And the point here is that if we pick a galaxy's stellar mass, as we go to higher and higher redshift, that gets to lower and lower metallicity. And I'll just note that this point here, this is now an observation of a direct metallicity using JWST near spectroscopy. And this is at redshift of 8.5. So here you can see the redshifted optical spectrum, and you have your O3 auroral line easily detected at redshift of 8.5. So this is now a common thing that is happening, which is amazing. In addition, this galaxy has been detected by ALMA in the C2 line. So we also have diagnostics of its ISM. So we have kind of even comparable, in some cases better information about some of these very high redshift, low metallicity galaxies than we do about things that are nearby in some cases. So that's exciting. All right, one last high redshift galaxy, low metallicity environment I want to mention is these damped Lyman alpha absorbers. So, right, these are objects where, we have a quasar at some high redshift that its line of sight intersects maybe the outskirts of a galaxy, maybe some debris around a galaxy. And we see this very strong absorption feature from the redshift in Lyman alpha in that galaxy. And these objects also often have metal absorption lines that you can detect, or maybe not often, but sometimes have metal absorption lines you can detect. And so there's a compilation here of the various metallicities measured as a function of redshift for damped Lyman alpha absorbers. And you can see this declining trend with redshift. This was actually the same data that was on that original compilation plot. So damped Lyman alpha systems, because they are just, happen to be in front of very bright point sources, we can learn a lot about their interstellar medium. And we will see them come up again shortly when we try to understand some aspects of the evolution of dust, which happens now. So I'm starting with dust in this low metallicity ISM discussion because dust is metals. And if we want to first understand, what changes about a lot of aspects of the ISM, we have to first understand what happens to dust. And what happens to dust actually seems quite dramatic. So I have a lot of slides about what happens to dust. I hope you're ready. Okay, so we're going to go through a couple of key properties of dust. We're going to talk about what changes about the dust to gas ratio. And I'm often going to switch back and forth between talking about dust to gas or as a function of metallicity or dust to metals. So dust to metals would just be the fraction of your heavy elements that are in dust. If it's constant, the dust to metals doesn't change. So the first thing we're going to see when we get into this is that dust to metals is not constant as a function of metallicity. So as you go to lower and lower metallicity, actually, it appears that a smaller fraction of your heavy elements are in dust. So just want to note, I will probably switch off in a kind of an annoying and maybe confusing way, and I will try to do my best not to, between dust to metals as a function, dust to gas as a function of metallicity, and dust to metals. We're also going to talk about the size distribution of the dust and its composition. And these are all critical properties of dust. They all change as a function of metallicity. Okay, so we're going to start with dust to gas ratio. And there are basically two approaches we have to try to understand how this changes. The first of those, I'm going to call the multi-wavelength observation approach. And this requires observing galaxies at a wide range of wavelengths. So we need to infer how much dust there is, and that we usually do with the far infrared. We have to infer how much gas there is, and that usually requires both 21 centimeters to get atomic hydrogen and carbon monoxide to get molecular hydrogen, because molecular hydrogen is super annoying. So we will combine those two tracers to get our gas. And then we also need metallicity to come from, these kind of H2 region optical spectroscopy observations. So this obviously is a big package of work. And we have a lot of information now, thanks to many people, including those in this room, about the dependence of dust to gas ratios on metallicity from this approach. The other thing we can use to measure dust to gas ratios and dust to metals, it's actually kind of dust to metals quite directly, is the depletions that we already briefly talked about. So the depletion actually just gives us the fraction of that element that's in dust. So this is a very kind of direct approach to trying to measure dust to metals. However, in order to measure a depletion, you have to have a bright point source that you can do a UV spectrum towards, or a redshifted spectrum for a damped Lyman alpha system, for instance. That's not always that common. And you have to make several assumptions if you don't know the reference metallicity of that object very well. And we have another expert on this in the audience, Julia, who you'll see her plots as well in here shortly. Okay, so starting with the first one, here's an example of the kind of data we need in order to measure dust from the far infrared. You don't need all of this, but this combines starting in the mid-infrared from WISE, Spitzer, the kind of the far infrared from Spitzer, and then Herschel. And this is M101, everyone's favorite weirdo. You can take all of these resolved maps, or you can take an integrated measurement of the entire galaxy, and then you can do an spectral energy distribution fit to the far infrared. And you can see an example of that here with one model. We have expert from Frederick as a major expert on the SED fitting and dust models as well. You'll see some of his plots shortly. But with this SED fitting, you can strain the radiation field, the dust mass surface density, aspects of the dust composition, potentially something about the size distribution from the shape of the infrared SED. So after that, we need to collect our gas observations. And this requires, first off, tracing the 21 centimeter hydrogen emission line. So this gives us atomic hydrogen. Here is a zoom in showing carbon monoxide in NGC 628. And then this is a map of H alpha, which is showing us where we can look to get ionized gas measurements and measure metallicity. So this requires a bunch of different telescopes. So a lot of work by everyone putting together these data sets of many, many galaxies with multi-wavelength information. So here's a very important compilation of dust to gas ratio, although just note, this is now gas to dust. I always say dust to gas, but sometimes you can just invert it. And that's all that's happening here. So you see the gas to dust as a function of metallicity. This green line is if you had a constant dust to metals, just a linear scaling of dust with metallicity. And what you see is that at high metallicities, maybe that works okay. There's some scatter, but in general, not bad. But then as you get to low metallicities, things deviate from that line by orders of magnitude, actually. So this is telling us that the dust to metals ratio is not constant, and in fact, varies a lot over this range of metallicities. And I just want to point out that this is for integrated galaxies. So we've collapsed everything into one measurement. In general, because galaxies have metallicity gradients, and because the ISM is not always distributed in, it can be in different radial distributions. Some of the scatter at the high metallicity points, especially, is probably due to the fact that there's metallicity gradients within these galaxies. So here then, at low metallicity, we can see things very strongly deviating here. So this is from Frederick's paper in 2021, showing, again, the dust to metals now as a function of metallicity, done with a quite different and sophisticated modeling approach. And you can see here again, at low metallicities, this dust to metals value is changing quite dramatically. So you'll also see on this plot, though, these pink points, which are from damped Lyman alpha systems, and they seem to be telling a bit of a different story. And I would say this is a question that there's still some, interesting tension and some things to learn. So let's talk briefly about dust from this depletion measurements. So the depletion itself, it is defined as the log of the ratio of the number of some element relative to hydrogen, and then the difference with the reference abundance. Sort of the Bible on this in the Milky Way is Jenkins 2009, which compiled a huge number of depletion measurements for the Milky Way and described them with a term called F star, which is basically an overall level of depletion assigned to each line of sight based on the observations of a number of different elements. And what you see here is the depletion of a bunch of different elements as a function of this depletion factor. And you can see these overall trends in the slope of this depletion of each element with F star. You can use that information actually to work out the differential composition of dust grains, because as you increase the depletion, right, you're putting some fraction of your carbon, some fraction of your oxygen, some fraction of your silicon, and so on into dust. And that gives you this idea of kind of what composition the dust is what the composition of the dust is that's being grown as these elements deplete. So in order to do this measurement, you need to have a reference abundance. And for the Milky Way, that's easy. You can go look at stars. For some nearby galaxies, it's relatively easy as well to look at stars. But for very distant objects like the damped Lyman alpha absorbers, you can't do that. So you need to figure out some other reference abundance to use. And the typical approach to this is to use a ratio of a very weakly depleted element like zinc to something that's heavily depleted like iron. And this lets you get back out basically an overall abundance that you can use. So this is a relatively important assumption. And Julia has done a lot of work, and we'll see that shortly, on looking into this assumption and cross-checking versus local galaxies. So in addition to the reference, you need corrections for unobserved elements. So in particular, carbon and oxygen are often not observable due to the redshift of where those lines fall that you can use to measure abundances. So this is important because these are the largest dust contributors by mass. So you have to make some pretty important assumptions there. And then you also need to know something about the abundance patterns versus metallicity. And in particular, if something like zinc, for instance, might have a different abundance pattern compared to iron. So this is a compilation from Julia's paper in 2022 showing measurements of depletion in the Milky Way, LMC, and SMC as a function of column density. So what this shows is that there are basically similar patterns in depletion between these three galaxies, even over a pretty wide range of metallicity. The depletion increases with density and column density here, which is consistent with grains growing in the denser gas. And you can see there's a factor of 3 or 4 increase over this kind of range of column density. And another thing that's clear from looking at this, and the compilation I'll show in just a moment, is that the dust to metals is actually lower in the LMC and SMC than it is in the Milky Way by using this information about what fraction is locked in dust. So here is a summary there of the fraction of metals that are going into dust as a function of metallicity for the SMC, LMC, and Milky Way. And you can see this overall lower dust to metals for the LMC and even slightly lower for the SMC. So this is how we get information about dust to gas ratios or dust to metals from depletions. And the summary here shows that there's still actually quite a tension between what you would find from the far infrared, so that's these kind of blue points, and what you would find from damped Lyman alpha systems, which are these red points. So whereas you see like that really steep drop to low dust to metals for some of the galaxies we've judged with far infrared and gas measurements, the damped Lyman alpha absorbers don't seem to have a quite steep drop that steep, and they generally have like a quite different behavior. So there's a lot of work to be done here, and in the question period we can also ask Julia tough questions about this. There's a bunch of possible reasons why this might not quite match up between the damped Lyman alpha absorbers and the multi-wavelength approach, but there's a lot to be learned there. So I want to talk briefly about why the dust to metals might change so dramatically. And to answer that, it's helpful to compare to models that try to implement all of the interesting aspects of the dust life cycle and tie that to galaxy evolution in some cases and see what you get out. So this is a really nice figure showing a summary of some of the dust evolution processes. So we think some dust is created in AGV winds, some in supernova ejecta. Dust can be destroyed by shocks and sputtering, and it can also grow by accreting elements out of the gas phase. So there's a bunch of different models that have attempted to put all of this together and understand some of the behavior we've seen in dust to gas as a function of metallicity. And I just want to show a few of those. So here is the plot from Remy Rouet again. And now overlaid are models from Asano 2013. And in this set of models, there's a critical metallicity, which basically happens where the rate of dust growth in the ISM, which is very metallicity dependent because it depends on, metals finding metals. And so this is kind of an n squared kind of a thing that happens. So There's a critical metallicity where the rate of dust growth exceeds dust production by stars. And so you switch from having basically stardust to ISM grown dust. So this is in the Asano model, this is related to a timescale for dust accreting metals from the gas relative to a timescale for star formation to occur in a galaxy. And so you can see this is a set of models with different star formation timescales and how that might kind of span the range of observations. Another approach to this was a simulation where this was done, so simulations by Zukowska et al. In 2014. And here you have bursts of star formation that occur that can then induce grain destruction and formation through supernovae. So not very much grain formation in that case, but a lot of destruction. And you can see some of those events with these little loops or jumps throughout this model. So here again, the answer has to, or the key point has to do with where dust growth becomes efficient relative to the other dust formation mechanisms. So this is from Frederick's very comprehensive and thorough. If you haven't read it, I highly recommend habilitation. I think that's what you call it, habilitation document, and shows a beautiful plot with another type of model, similar components, and again shows part of this low metallicity region where you have dust condensation from stardust, whether that's supernova or AGB stars, a critical metallicity, and then a transition to where growth in the ISM is efficient. So a lot of these models kind of come to relatively similar conclusions about the fact that grain growth becoming efficient is one of the important things that transitions from low metallicity dust to higher metallicity dust. And I just wanted to point out a couple of other models that don't exactly match that particular conclusion. So there's models by Feldman et al., which is a competition. I mean, it involves dust growth, but a competition between dust growth and dilution of the metallicity by inflows. Then there's a model by Priestley et al. Showing that if you increase the dust destruction efficiency at low metallicity, you might also be able to explain these trends without the need for very efficient dust growth. Okay, so I want to just summarize about dust to gas ratio real quick. And that the main points to take away here are that at relatively high metallicity, we have a pretty constant dust to metals on global galaxy scales. But if you look within a galaxy, the dust to metals does vary. So you get dust to gas ratios that are different in different parts of the ISM. So there's a dependence on column density. There's probably a dependence on volume density that we have a hard time measuring that. And there's a dependence on where you have a lot of H2. So at low metallicity, there's a drop in dust to metals. And this is generally quite agreed upon. And a lot of models attribute this to efficient grain growth kicking in at some metallicity, but the low metallicity galaxies is not efficient yet. And so they have a lower dust to metals ratio. But we have a lot to do yet, I think, to understand grain growth. So I think I want to, maybe I'll just get through a little bit more before we do questions. Is that okay? Okay. So I want to talk about a few additional things about dust before we have some questions. First off, the size distribution of grains also changes. And we can see that when we look at the extinction curve of dust. Does anyone, think for a moment about looking at this extinction curve? How would you tell that for the low metallicity one, the SMC up here, that the size distribution had changed? Any thoughts? Well, the main point is that dust grains are best at absorbing or scattering light at around their size. So if you have this continued increase, and sorry, I should have pointed out these weird units. This is the inverse microns. So this is the far ultraviolet over here, on this part of the diagram. So as we continue into the far ultraviolet, the fact that the extinction in the SMC extinction curve continues to increase tells us there has to be more small grains to keep doing better and better at blocking those wavelengths. So from this extinction curve, we can see that the SMC has a lot more, or has on average, smaller dust grains than what's in the Milky Way or the LMC shown here. You can also learn about this actually by the temperature of the dust grains in dwarf galaxies. They tend to be hotter, and this also provides some evidence that grain sizes on average are smaller. Even more than the size, though, what you can see as we look at these low metallicity extinction curves from the SMC is that we lose the 2175 angstrom bump. So each of these little chunks is a different sample of extinction curves. Underlying the dashed line is the Milky Way for comparison. And you can see that in all but a few of these extinction curves from the SMC, there is no 2175 bump, or a very weak 2175 angstrom bump. And the possible exception are actually two extinction curves that come from a little molecular cloud in the southwest bar of the galaxy. And one that comes from, I don't know if it's on here, but one that comes from a random spot that no one really understands. So the lack of a bump also shows up when you look at extinction curves towards gamma ray burst host galaxies. So these, you get a really temporarily bright point source that you can do spectroscopy towards. And you can see that in many of them, you also have this steep extinction curve and the lack of a bump. So there's recent work that actually shows that the presence of a bump in some of these GRB extinction curves is correlated with seeing neutral carbon absorption, which is an interesting indication that we're looking at denser gas along those lines of sight. In addition, okay, so extinction curves are great. They're very informative, but we have a very limited set of objects for which we can use to measure those. The other thing you can do is try to measure something called an attenuation curve, which is really similar, but rather than a single point source, which is a nice clean measurement of the light that is removed from the line of sight by whatever process, in an attenuation curve, you have a whole bunch of stuff, and you have to deal with the effects of geometry and scattering into your beam sometimes and various other radiative transfer effects. But with careful approaches to this, you can interpret these attenuation curves. And there's evidence now from a variety of different papers that suggest that at low metallicity, the attenuation curve also lacks the bump and is steeper, much like what we see in the extinction curves. And there's a recent paper by Irene Chevai that correlates the bump observed in attenuation curves with the redshifted emission from polycyclic aromatic hydrocarbons, which shows up for these galaxies at 24 microns. Originally, it's at 8 or so microns. So there's some indication here that there's a correlation between those two things. And indeed, one of the likely explanations, though this is controversial and many people have opinions, is that the 2175 bump is potentially related to pause. So this is some laboratory data that shows a plausible looking bump that comes about from mixtures of pause observed in the lab. So the lack of a 2175 bump in the extinction curve may be reflecting the lack of pause in this galaxy. And indeed, what we see when we look at low metallicity galaxies, and this is a topic that many people here have thought about, is that the emission features in the mid-infrared that come from pause disappear. So this is a stacked spectrum of galaxies as a function of metallicity. And you can see dropping down to these very low metallicities, you have very little PA emission coming from these galaxies. And this is not a problem of illuminating them. They are perfectly happily illuminated. We can figure out something about the actual fraction of the dust that's in the form of pause through far infrared SED modeling. And this is a compilation from the Kingfish and Singh survey showing something called the PA fraction, which in the Drain and Lee models, at least, is defined as the fraction of dust in the form of pause with less than 1,000 carbon atoms. And you can see steep metallicity dependence. There's a bunch of scatter up here at high metallicity, but then at low metallicity, it's always low. And this is kind of corroborating the fact that, we see the emission features disappear, and this is truly a change in the fraction of the dust that's in the form of pause. And this can also be seen with other approaches to dust SED modeling and other definitions of what you would consider pause or various types of aromatic carbon material. And so this is from some of Frederick's work showing the mass fraction of small carbonaceous grains as a function of the intensity of the interstellar radiation field and metallicity. Okay, so I have a bunch more to say about pause. Should I finish the pause before questions, or do questions and then finish the pause? What do you guys want to do? Questions? Pause? Questions. Okay, let's do questions, and then I'll come back to more about pause just after this.
Questions? Anything so far? The back from the south?
Yeah, not on.
Thank you. Oh, it's very interesting topic, and I'm not the expert in the metallicity. I just have some common sense question I would like to ask.
Sure.
So for the metallicity, so it seems it increases with the stellar mass, but when it comes to the high mass, there's a plateau. Is there a reason?
Well, it may be the case. What's the reason for the plateau at high metallicity? Good question. I think it's probably lower star formation efficiency. You at that point don't have that much more gas to turn into stars, so you end up with probably fewer kind of like big increases in relative to your existing stellar mass in how much metals you put back into the ISM. I don't know, is there an expert here about mass metallicity relationships? I think that's probably related to the explanation, but I'm not 100% sure.
Okay.
It's actually in the analytic solution of in-fall model has this saturation already. So the maximum metallicity you can get is the net yield. So that because the stellar mass, even if you make a lot of stars, some of the matter come back to the ISM. So you can't convert all matter into metals.
Oh, that's my another question. So like when we are talking about the metallicity of the galaxy, do we just assume that's gas-phase metallicity, as like gas metallicity, not star metallicity?
You can measure stellar metallicities, definitely, and you can, people use those for a lot of different things. But yeah, that wasn't going to be my focus in this talk. But stellar metallicities, I believe there's also a stellar mass, stellar metallicity relationship, and various other measurements of kind of the chemical enrichment from starlight, that you infer from stellar spectra.
Okay. So if we have the map of the stellar metallicity and also the gas metallicity, are they correlated somehow? I don't know.
That's a good question. I don't think they always are. No. You can have, I think you can have plenty of regions where the stellar metallicity is high and the gas metallicity is low. There probably is an overall correlation. This is a little bit out of my area of expertise. So
just one last new question. Where does that 12 come from?
So it's just handy because if you add 12 to the log of whatever x over h, it's always everything is basically positive.
Okay.
You have to get to really rare elements before that becomes negative. So it's, I think, just handy for bookkeeping. Probably you didn't want to miss any minus signs. It's a historical thing.
Okay, thank you so much.
There's one back in.
One more, just next to you.
Thanks. I'm wondering if there's any like caveats to using oxygen as a tracer of metallicity? Like, could some of it be missing and we're not getting the full picture, or?
Yeah, so there is some oxygen that is depleted into dust in H2 regions. It's not a huge amount. And so if you're being careful, you definitely would correct if you want like a measurement of the, undepleted abundance of oxygen, you would have a small correction to account for that. I mean, there are also there's a whole can of worms we can open about the troubles people have with direct electron temperature dependent metallicities using oxygen. There's like quite a bit of stuff about, temperature and density inhomogeneities in H2 regions that give you kind of biased results when you try to use the optical auroral line to judge the metallicity. But we don't have anything better. So, I mean, there's a lot of things to worry about, but I think for many applications, and this is not all applications, but for many, it's pretty good.
Thank you.
Brent, do you disagree? Any other metallicity people disagree? Nope. Okay, I have to cough real quick. I'm gonna turn off my.
Brent, any other questions? In the back first, and then you was next.
A very nice talk. I'm like really informative. I had a follow-up questions to what you asked. The first question is when some of the oxygen is getting depleted in the H2 regions. So is this possible that we can trace that oxygen or the depletion of dust and somehow can be translated into temperature of dust and then we can like regain it or something?
I think the way people tend to find the oxygen that's depleted still in H2 regions is they do something like a metallicity from the young stars that are in that region, which the dust is no longer a problem for those, and then compare it to what you get from modeling the H2 region lines. I don't know that dust temperature has much to do with it, but we can measure, something about the dust temperature from the spectral energy distribution in the infrared. But yeah, I'm not, I mean, it seems likely that, there would be a dependence on how hot the dust is. And in some cases, you may have an H2 region that gets hot enough that you can liberate a lot of the elements that might still be depleted into, back into the gas. But this is also not something I have a lot of expertise in. So it's an interesting question. That's probably all I can tell you. But if anyone else in the audience can tell you more, please speak up.
I have more questions actually. I'm sorry. Okay, so second question, we are having like in slide 51, I guess, we are having the depletion, how to measure depletion using this formula. So the one which is on the right, like the second part of the formula, that is the refresh abundance, that is coming from the abundance pattern, right?
So it depends on the situation. If it's the Milky Way or nearby galaxies, it could come from stars. If it's going to be a DLA, it probably does. You refer back to zinc, and we can pester Julia about this if we want right now. But yeah, you would use something like the zinc to iron ratio and then work out what the reference abundance was from that.
I think I need to talk to you later on.
Well, you need to talk to her, but yes.
Yeah, sure. And there's one more thing which was saying about the critical metallicity, which says that at which the rate of dust mass growth exceed the dust production rate by star. That when we say dust production rate by star, that means supernova explosions and kind of
and evolved
outflow.
Stars. So AGB stars produce dust in their outflows. Yeah.
Thank you very much.
So for some of the systems that have very low metallicities, like the first ones that some of the first ones that came to mind for me were ultra faint dwarfs. And so And like that really pushes the boundary for the mass metallicity relationship as well, which isn't really, it's very fuzzily defined below like 10 to the 5 solar masses roughly. So for these really low mass and like low surface brightness systems, like how are the metallicity calculations even made?
So those will all be stellar measurements.
Okay.
So ultra-faint dwarfs don't have any gas. So they will be devoid of gas, and you measure actually probably individual stellar spectra to get those answers. So yeah, that's a very interesting type of galaxy, but it's got no ISM. So, you know, what are we doing?
Yeah, it's also iron abundance too for ultra-faint
Yeah.
dwarf galaxies. That's another maybe causing some difference. Any other last quick question? So the trick is while others asking questions, you contact me, you look at the chair and give me eye contact. In that case, microphone will come to you. That's the trick. Anyway.
All right, should we keep going? Or you have something,
Do
Troy?
you wanna, are you okay to continue? No?
Yeah, I think Jerome had a question though.
What is the current rate of metal enrichment? How long would it take to double the metallicity today?
That I do not know off the top of my head. That is, I mean, we are certainly in the Milky Way, we are in that saturated part probably of the mass metallicity relationship, right? We're not, I don't think we're, I mean, right, the sun is 4.5 billion years old and basically very close to the same, almost the same metallicity as the gas. So the timescale to double the metallicity in the Milky Way would be very, very long, if infinite, maybe. I don't know.
Among the nearby stars, the sun is slightly more enriched than the average of solar neighbor stars.
Got it. Was that approximately accurate though, my answer? Yeah. Okay. All right, well, let's get back to pause, which are the best type of dust. So we have established that as a function of metallicity, there is a deficit of pause as we get to the lowest metallicity, and we want to know maybe why. So there's a couple of potential reasons. It may be that there's enhanced destruction of the pause from harder or more pervasive UV fields, or they might not form efficiently, depending on how they form. We actually don't know how they form. So there's a couple of options here, and I want to go through a little bit of the evidence for both of these. So this is a key result that came about even early on with ISO and Spitzer observations, which is that the abundance of pause, so relative to the other dust grains, and this is emission of pause relative to continuum emission, has correlated and drops off with the hardness of the radiation field in H2 regions, judged by the ratio of neon 3 to neon 2 mid-infrared lines. So this might suggest that destruction by harder radiation fields could be important. These two things are correlated. Oh, thanks. However, the question might be how the radiation field in the H2 region impacts the pause, which are generally outside of the H2 regions. And so I think there's still some questions there about to what extent the radiation field hardness actually impacts the pause. So one case where we can look at this in a lot of detail is the Magellanic Clouds. And here is the beautiful SMC image with Spitzer. So we went and looked at this using SED modeling to make a map of the fraction of dust in the form of pause across the Magellanic Clouds. So this is the SMC. We also modeled the LMC. And so this is a 10 parsec resolution map of the PA fraction. And what you can see within this galaxy is that there's a lot of variation, even in the SMC. So there's some places where it's quite low. There's some places where it's relatively high. And it's not, because this galaxy is at basically one metallicity, it's quite uniform. This tells us that metallicity is not the only factor at play in what's going on in setting the PA fraction. So here's a comparison of both the LMC and the SMC and their average PA fractions. So we can compare that to where they sit on this plot from before, and they nicely agree with where you'd expect based on their metallicities. But we can also go one step further and look at the environmental trends that set the PA fraction. So we can divide the galaxies up by their ISM environment. For instance, here is a selection of only H2 regions defined by optical observations. And so you can see that in those regions in both galaxies, the PA fraction is quite low. We can then go a bit further out and select diffuse ionized gas. We find slightly higher, but still low PA fraction compared to the average. We can then select neutral gas without CO traced molecular clouds. And we find a higher PA fraction now over that. And lastly, we can select the parts of these galaxies that are molecular clouds. And we actually find this by a little bit the highest PA fraction. So in general, what we find is that the molecular and diffuse neutral gas has the highest amount of PAs, and then it drops off when you go into the diffuse ionized gas and the H2 regions. So this tells us that PAs are destroyed where there is ionized gas, but the neutral phase of the ISM actually has kind of the baseline PA abundance pre-destruction, and it can be quite high. You'll have noticed that in the LMC, it was getting up to kind of comparable values to what we see in the Milky Way even. So we can also look at how the PA fraction changes as you get into regions with ionized gas or with high radiation field intensities. And these are now normalized by kind of representative average values. And what you see is in both the SMC and LMC is a kind of a consistent trend of the decrease in the PA fraction as a function of ionized gas and radiation field intensity. So between these two galaxies, which are a factor of a few different in metallicity, they or 2 to 3 different in metallicity, they have not highly metallicity dependent destruction. Of course, this is a small range compared to that previous plot where you got down to quite low metallicities for a lot of those galaxies and quite intense radiation fields. So this may not quite approach that level of destruction. I did want to mention that one of the things we've already learned from JWST is that the destruction of PAs, we can now make these 10 parsec resolution type maps using a mid-infrared tracer of the PA fraction in galaxies out to 10 to 20 megaparsecs. So we have a lot more options for understanding PA destruction now. And this is a paper by Oleg Egorov, where he measured in the H2 regions identified in FANG's galaxies what the PA fraction was. And this is a mid-infrared tracer, so it's not quite the same as QPA, but we think they're generally correlated. And you can see a quite steep drop as a function of the ionization parameter of the H2 region. And there's actually not really any difference over at least the small range of metallicity that we covered. So this is suggesting, you know, the H2 regions, the PAs are destroyed in a way that's not particularly metallicity dependent, though it would be nice to have a larger range of metallicity in which to measure that. I'm sorry, I have to cough, so I'm going to turn off the mic for a second. Is it back? Okay, good. All right, so one thing I think is interesting is looking at that diffuse neutral gas and that kind of baseline PA fraction we saw. In the LMC, it was, you know, high, it was like 4.5%. And in the SMC, it was much lower. So it's interesting to try to explain what could explain this highly metallicity dependent kind of neutral PA, ISM QPA. And it's probably not input from stars, because it seems to actually be the case that as you go to lower metallicity, your carbon stars will input more carbon-rich dust. So this would probably explain the opposite thing. It does make some sense that if you go to lower metallicity and if PAs are grown in the ISM somehow, then there would be a strongly metallicity dependent PA fraction. But we don't know exactly how PAs form, I would argue. They may form, there's some evidence for gas phase formation in dense clouds in the Milky Way. They may form from shattering bigger grains. They may form primarily from AGB star atmospheres. They may form in a variety of ways. So I think that's one of the main things we need to learn hopefully in the JWST era to understand what PAWs are doing. And I just wanted to make a few last notes. And I know this is a lot of stuff about PAWs, but you asked me to talk, and that's my favorite thing. So yeah, sorry. PAWs are wonderful because one of the things they do is their vibrational bands actually help us diagnose something about the characteristics of the grain. So grains, the distribution of grains, that includes their size, their charge, maybe even their structure. And the resolution we're going to get now with JWST spectroscopy is really going to open a lot of windows to studying all of those aspects of PAWs. This is a beautiful figure showing it's a low Spitzer resolution, kind of what the main features are. And the ability of PAWs to emit in each band is dependent on their charge and their size. So you see here neutral and ionized, and then function of size. And this is a kind of a coarse model that builds on laboratory and observations. There's also a very detailed investigations of laboratory and quantum chemical calculations of individual PAWs to learn about what their spectrum, predicted spectrum is. So just to end our kind of like low metallicity PAW section, one thing that I'm really interested in understanding is that when we looked at PAWs in the SMC, they all tended to have band ratios that suggested they were smaller and neutral compared to higher metallicity PAWs. And this is something I don't think we know exactly the reason why this is the case yet, but we are about to see lots of low metallicity PAW spectra. So my hope is that we're going to have a lot of knowledge about all the ways that bands vary in low metallicity environments and tell us what this means. So let me summarize about dust. Grains become smaller on average. We see that from the ultraviolet extinction curve. We see that from the temperatures of dust grains in various low metallicity galaxies. The 2175 angstrom bump in the extinction curve becomes rare. This is probably closely tied to the fact that PAWs themselves become rare. The dust to gas ratio drops quicker than linearly with metallicity, so the dust to metals ratio drops. And this may be related to inefficient dust grain growth. And PAWs become very hard to find, but below metallicities of 12 plus log over H of around 8. And they may be smaller and more neutral potentially in some cases, and they may be concentrated in the vicinity of CO gas. So with that, I want to move on to talk about the effects of low metallicity on the ISM. And I'm going to have to go a little quick. So there's a couple of key points that I want to make. So when you go to low metallicity, a few things change. One of them primarily is the balance between heating and cooling in various ISM phases. So this is just a little summary of heat sources and coolants in different phases. The red things are things that vary a lot with metallicity. So collisionally excited metal emission lines, C1, C2 and O1 fine structure lines, photoelectric effect. So the game we're going to play in a lot of circumstances is we are changing our heating and we're changing our cooling. Which one of them wins in terms of like how the ISM responds? There's a lot to be learned there. And just for reference, here is a illustration of the heating and cooling balance in ionized gas. The largest component of the cooling is these collisionally excited emission lines. Here's another, this is cooling per hydrogen molecule in molecular gas. And the dominant component of this is carbon monoxide and various other molecules that dominate the cooling. Another key point is that when we go to low metallicities, stars tend to produce harder spectra. And that's because they also lack the absorption lines from metals in their photospheres. And that allows them to produce more shorter wavelength photons. So this is a compilation from the BPAS models showing the photons at short wavelength normalized to 1500 angstroms. You can see this increasing as you go to lower metallicity. And this is directly reflected in the ionization state of H2 regions. And you can see here neon 3 relative to neon 2. So this is tracing kind of the ionization in these regions as a function of metallicity. And this is what you see in like higher metallicity galaxies. And then way up here you have, for instance, blue compact dwarfs, which are very low metallicity starbursts. And then lastly, dust, as we've just thoroughly gone through, changes quite a lot. Particularly, the dust to gas ratio drops. And this changes many things about the ISM, because a lot of the structure of the ISM is you could classify as a photodissociation region, where UV photons are dominating a lot of the processes that are going on. And because the dust to gas ratio has changed, you have a lot longer path length before you get to an extinction of 1. AV of 1, where a substantial fraction of your UV photons are now gone. So this means that you have quite a bit of change to anything that requires dust shielding. And on the topic of PDRs and how that changes at low metallicity, I think there's a lot to be learned here that we are going to have really a lot of fun doing with JWST, because there are many competing effects that come into play when we're talking about changing the metallicity. So the radiation fields are harder and less attenuated. We have less dust extinction. The heating rate is going to be, who knows, because the heat sources of photoelectric effect off of small grains will go down, but maybe the grains are more neutral, so they're better at photoelectric heating, so maybe it goes up. But then the cooling, which relies on metals, goes down. So there's a lot of competing effects. And I don't think we know yet the final answer about what the resulting PDR structure and how it will be different is like. And this is something that will be great to understand with JWST. So moving on from there, I'm just going to go really quickly through ionized ISM. There's a lot of fascinating changes to the ionized gas, but I want to talk primarily about molecular gas, so we're going to speed through a little bit. Here's a bit of a summary of what we know about ionized gas at low metallicity. In general, you have higher electron temperatures, harder and more pervasive radiation fields, a higher ionization parameter, and perhaps most importantly, a larger filling factor of ionized gas. So the ISM becomes more porous, it appears, to ionizing radiation, and so you get a much more pervasive diffuse ionized gas component. So on the topic of electron temperatures, just going back to this plot, here is actually a summary of the individual collisionally excited emission lines that are contributing to cooling at the Milky Way's metallicity. If we compare the heating, which is not that dependent on metallicity because it's just photoionizing hydrogen, so, not that metallicity dependent, to cooling, what you find is that the temperature of an H2 region should get much hotter. This is where cooling and heating balance in 1/10 solar metallicity situation. So almost 15,000 Kelvin. So that is one of the main changes we see. Electron temperatures are higher, and that makes it easier to excite the auroral lines. So you can see the auroral lines in many more H2 regions at low metallicity. In addition, from the far infrared lines, so this is the O1 88 micron and C2 158 micron, what we learned from surveys of dwarf galaxies is that the O1 line is actually O3 line is actually one of the brightest lines observed from dwarf galaxies. You can use multi-line modeling, so many different emission lines, far infrared, mid-infrared, optical, together to try to understand what drives this. And it appears that to explain this, you need to have higher ionization parameter and a more porous ISM to ionizing photons. So this means that because of the lower attenuation potentially, and maybe also because of changes in the density distribution or clumpiness, you have photons, ionizing photons being able to get escape from the immediate vicinity of their H2 region and produce a more pervasive ionized medium. So this may be related to actually an important question at high redshift, which is how do you get Lyman continuum photons to escape and power reionization? So there's a lot of interesting crossovers now between local dwarfs, where you can see this in a lot of detail with many, many lines, and some of the high redshift galaxies, which you're now observing to have also these high ionization parameters and interesting ionized gas properties. So I wanted to point out IC10, which is a really interesting nearby dwarf starburst galaxy. And this was observed with Sophia, I believe. Yes, not Herschel. So Sophia, and in the far infrared, and using multi-line modeling of a set of many emission lines. You can see that here. This is results looking at the ionized gas state in IC10. So I wanted to point out this result here, which is basically this depth parameter in this particular modeling setup basically suggests finding a value less than 1 means that these regions are matter-bounded H2 regions where ionizing photons can actually escape and contribute to this more kind of extended diffuse ionized component. This is also seen in the Magellanic Clouds. So this is a observation of N13, I think with Herschel this time. And this shows the 0188 micron line again. And you can see quite a lot of diffuse extended 03 emission coming from this region. So this suggests that there's a lot of maybe low density channels where things can escape, high porosity in the ISM. So that's all I'm going to say about ionized gas. I think there's a lot more to say, but I'm much more focused in a lot of things on molecular gas. So in the question session, if people want to add anything about ionized gas and dwarfs, please feel free to speak up. We have learned a lot based on observations from Herschel and Sophia, and in particular the Dwarf Galaxies survey, which did a lot of work on that topic. Oh yeah. Oh, I don't know if we're doing questions now, but that's cool.
How much would you evaluate the porosity or clumpiness roughly?
How much would I evaluate it?
Yeah. On the ionized region and the PDR.
How much? Well, I think maybe the relevant thing here is this quantity that measures some kind of depth, basically the transition between the matter bounded and the radiation bounded is at 1. So there's evidence from this kind of modeling, at least, that you're in the matter bounded situation.
And on the previous slide?
The previous slide. Oh, I'm not 100% sure. I should have.
So one before.
Oh.
Yeah, this one.
So this, I think the relevant quantity here is the covering fraction of PDRs. So this is finding that the covering fraction is not 1. So not every region that has ionized gas has a PDR surrounding it.
So what is a typical value?
Oh, that I'm not sure of. I think it would, do you happen to know off the top of your head? We're gonna have to look that one up. This is not my main area.
Okay. Fine. Thank you.
Yeah. All right, so moving on to the atomic ISM, we are again in the situation where our heating and cooling balance is thrown off. So our heating source this time is photoelectric effect from dust, and our coolants are metals. So both of those things are changing as a function of metallicity. There's been a lot of work over many years looking at the implications of this on the thermal instability model for where you have the cold and warm neutral medium phases. This is from Wolfire 1995. And here you see varying the metallicity or fixed metallicity with a variable dust to gas ratio. And here's metallicity and dust to gas ratio linearly related. And what you can see is that as you go to lower metallicity, you're pushing this phase curve to higher and higher pressures. So what that means is that when we, have a situation where we have cold and warm neutral medium, we will tend to be at a higher pressure. We'll actually, you can't see it from this plot, but I'll show you another plot later. You would tend to have cooler temperatures. And in this case, you may get into a situation where you end up with just less of your ISM being able to produce cold neutral medium if you have to have very high pressure, for instance, in order to be in that stable phase. The other thing that's worth mentioning, and this is accounted for in some of these models, is that dust and pause are not linearly tracking each other as a function of metallicity. And when you have pause, they actually dominate the photoelectric heating. So this is heating as a function of grain size. And so things, in this region, in fact, most of this plot would be considered pause. So we may end up in a situation where we become particularly ineffective at photoelectric heating if we have destroyed many of our pause. Also, if your pause become ionized or charged, they might become harder. It's harder to eject another photoelectron, so they become less efficient heaters. So that may be a competing effect if low metallicity pause tend to be more neutral. They would be better at photoelectric heating. So something to keep in mind. So this is a recent modeling effort looking at this phase curve as a function of metallicity. And I wanted to point this out because this attempts to include the nonlinear scaling of dust to metals or dust to gas ratio with metallicity. And what's interesting is that as you start off, the phase curve in black is Z of 1. This is the phase curve for the first step lower metallicity. And then it turns around and moves higher and higher. And this is very low metallicity up here. So what you can do with this, though, is actually look both at where the pressure for this equilibrium phase balance is and what the characteristics of the CNM are. So this is the temperature and pressure, temperature in the color table, and pressure and metallicity. And we can see that actually, if we start at Z of 0, or solar metallicity, and move down, there's actually cooler CNM as we get to Z of 10 to the minus 1. So the changing effects may lead to colder CNM, higher pressure, and potentially less CNM if you have to have, a few high pressure regions where you have the ability to make cold neutral medium. So I just wanted to quickly review some of the observations that are relevant here. So this is absorption measurements of H1 towards background sources behind the SMC. The first version of this was done in 2000. And in fact, they found temperatures of the CNM about 40 K, which is actually substantially less than what it is in the Milky Way. And the CNM fraction is pretty low compared to the Milky Way. It's more like 30% in the Milky Way. This has now been done better with the Australia Telescope Compact Array. And then you can see here, the CNM temperature is again low CNM fraction. And this is done even better now by GasCap, the pilot survey of absorption towards the SMC, where they found even lower CNM fraction of 11%. I'm going to go really quick through this, but the other thing that's cool is you can use ultraviolet absorption lines from neutral carbon to judge the pressure in the ISM by comparing the excitation in within the ground state fine structure levels. And you do this with ultraviolet measurements. And this is work by Welty et al. In 2016. And they found that the thermal pressures in the LMC and SMC CNM are several times higher than in the Milky Way. So this agrees with that kind of picture. Putting this all together, we have evidence for lower CNM fractions, colder CNM temperatures, and higher pressures in the Magellanic Clouds. And this is kind of in good agreement with what you might expect based on assessing all of the heating and cooling terms that change with metallicity. And it's also, I skipped over it real quick, but the transition to H2 occurs at a higher surface density here. So I've talked for a really long time, and I'm going to speed rapidly through a bunch of stuff about molecular gas now. So the key point for molecular gas is that because of the decreased dust shielding, things that rely on dust to avoid photodissociation, like CO, have a major impact in low metallicity conditions. While H2, which is so abundant that it can shield itself, doesn't really feel that impact quite as much. So this leads to a situation, and this is a really nice cartoon version from Madden et al. 2020, where in the Milky Way, you're gonna have most of your cloud having CO in it, in a thin layer without CO. But in a low metallicity galaxy, you might have a very large part of your cloud, which is CO dark H2. And we've already heard a bit about this from Julia the other day. So this can be predicted in simulations, and we actually even saw this plot, so I'm gonna go pretty quick. If you change to SMC-like from Milky Way-like dust to gas ratio, you have a much smaller fraction of your cloud producing CO emission. So what we need to understand is basically how much CO dark H2 is there if we want to understand things about the molecular gas, the low metallicity, and what is the CO bright component doing. So there's a lot of ways to attempt to measure the CO dark H2. We're going to have a very rapid look at these. You can do this with dust if you assume something about the dust to gas ratio, or you measure it locally in a resolved way and apply it everywhere in the map. Key issue here, do we know actually how the dust to gas ratio behaves as a function of metallicity well enough to do this? And do we know stuff about how the dust properties change so that we can accurately model the dust surface density? You can do this with C2. In fact, most of the carbon, when it's not in CO, should be in the form of ionized carbon in these regions. So if you were able to separate out all of the other stuff, the part that's coming in the C2 emission that's coming from all of the other parts of the ISM, then you could potentially trace the H2, CO dark H2 with C+. So that has been done in the Magellanic Clouds, found a large fraction of the H2 being traced by C+. It's been done using velocity resolved observations where you have a nice handle on what's coming from the different phases because you can compare with H1, you can compare with CO, you can find the stuff that's really not traced by either of those components. You can also do this by modeling many different lines in unresolved galaxies. And this was a work done by the Dwarf Galaxies survey, and found that the fraction of the C+ coming from ionized gas is actually really small in these low metallicity galaxies. And from that, you could infer the amount of CO dark gas, or the H2 from C+, and combine this with what is observed in CO to work out a conversion factor. And this shows a compilation of many different conversion factors from a variety of prescriptions. And here you can see what's observed using the C+ in the red dots. There's some really interesting stuff just last week, even, I think, came out about how the clumpiness of the ISM may impact that CO dark H2 fraction. You can also look at this with C1, and in particular, absorption lines in damp Lyman alpha systems are a very useful tool there, and show that you actually will have a metallicity dependent alpha C1 as well. And that may be something that is useful to trace molecular gas. One last thing you can do here is invert the Kennicutt-Schmidt law and work out from the observed star formation rate and an assumed depletion time, how much gas you should have, and then compare with molecular gas you observe in CO. And this gives you a conversion factor. So that was a lot of tracing of CO dark gas. One more here is actually directly a limit on CO in a very high redshift, or in a high redshift damp Lyman alpha system. But I want to just show all of these together. So I think the takeaway point on this is that everyone agrees there is a lot of CO dark H2, a ton of it. It's really difficult though to get estimates of how much there is that agree with each other. So you can see that as you go to low metallicity, there is quite a substantial spread in the possible conversion factor you would use that's appropriate here. So we have learned a huge amount about CO dark H2. There's a lot left to learn about how much of it there exactly is. So just to note, we also, the corollary of a lot of CO dark H2 is that there are tiny clumps of CO bright H2. Most of the cloud is CO dark. So here we have some observations that show us these tiny parsec scale clumps of CO bright H2. This is seen also in NGC 628, sorry, that was WLM, a dwarf galaxy in the local group. This is 6822. Another observation of these tiny clumps. Here is now big surveys of the SMC. Big surveys of the SMC showing these tiny clumps. And I'm going to skip ahead to just summarize that when you look at these tiny CO clumps that you do find at low metallicity, they appear to have still a higher conversion factor than the Milky Way, but not dramatically higher. So not the kind of answers you're getting if you try to take into account the CO dark gas. So there's now quite a few observations showing these tiny parsec scale kind of clumps in molecular gas. So to summarize on molecular gas, most of the H2 is CO dark at low metallicity. This can be seen observationally with a variety of techniques. Everyone seems to agree on the dominance of the CO dark H2, but I think the exact amount is still quite uncertain and how you get that value. And then the CO bright part is in these tiny parsec scale clumps where the conversion factor is still higher than the Milky Way value, but not ridiculous. So at the end, I think I have just a couple of minutes left. I just want to point out a few things about the future. So this is an amazing map of NGC 346 and 66, an SMC star forming region that I spent a lot of time looking at as a grad student, and many people I think have looked at a lot. This map has a resolution of something like 0.05 parsecs. So we're seeing dust emission, gas emission in low metallicity conditions at very high resolution in the Magellanic Clouds. In the local group, other dwarf galaxies, we get parsec scale resolution. In galaxies out to 10 megaparsecs, we get, 10 parsec resolution in some tracers. So we have a huge amount of learning to do using JWST observations of the low metallicity ISM. We have new tools. We have high resolution spectroscopy. We have photometric bands that trace a whole bunch of ISM relevant things. We have new diagnostics of pause. That's very exciting. And you can find individual pre-main sequence stars and YSOs, just like people do in the Milky Way, but now in low metallicity galaxies. So I think we're on the verge of a lot of really cool insights about the low metallicity ISM. This is another thing that came out, I think just today or yesterday, which is NGC 6822 observed with MIRI. And I mean, this is all a lot of pause. There's a bunch of pause, and maybe that's a supernova remnant. I don't know. There's some really cool things in this map. And of course, lastly, we are going to have now a lot of other people who are suddenly interested in the low metallicity ISM, because things like direct metallicities can be measured for galaxies at redshift 8.5. And you can go look at them with ALMA and measure far infrared emission lines, just like we do in nearby galaxies. So did in nearby galaxies with Herschel and Sophia. It would be nice to be able to do that again someday. So with that, I just want to end on a couple of points. Low metallicity has a really dramatic impact on the ISM. It alters the dust a lot, decreases the shielding changes heating and cooling, all kinds of things. We can see that dust to metals is not constant, it drops at low metallicity. We lose all the pause, the grains become smaller, the composition changes, and a lot of this might be due to the efficiency of grain growth in the ISM becoming lower and lower at low metallicity, just because it's harder to have, things meet up to grow grains when you have very low abundance of heavy elements. Ionized gas is hotter, high ionization, and more porous. Atomic gas has colder and less common CNM and higher CNM pressure. And this is generally in line with what you might expect from heating and cooling balance, although I will emphasize that we don't know all of those changes yet that might be occurring. And there's a lot of competing effects, and there's interesting things to be dug out there still. Molecular gas, mostly CO dark with tiny parsec scale CO bright clumps. And there's still some work to do on nailing down that actual fraction of CO dark H2. And there's a lot for all of us to do in the near future with JWST and ALMA. So thank you very much.
Thank you very much. It's really a lot of new stuff ongoing. That's great. Questions? Let's start.
Yeah, thank you. I have a question relative to dust. You didn't talk at all about silicate dust.
About what?
Silicate dust.
Oh,
which represent in our galaxy 75% of the dust mass. So is it because it's more difficult to observe, or because you just assume that it wouldn't change with metallicity?
I mean, I would like to not assume that. It is harder to observe though. So, it doesn't have any nice emission features usually in most circumstances that we can use to identify it. I think that there's probably some interesting things to be learned from depletions, and but I am certainly not on top of exactly what those are. But I think that it's a subtle effect from the SED modeling to try to pull out the change between in the SED that represents silicate versus carbonaceous dust. I mean, maybe you have opinions on that, Frederick, but I think it's a lot harder to know about that compared to pause, which are just like, here I am, now I'm gone. It's really easy to see those comparatively. So.
Any more questions? In the middle, and then you are the next.
So obviously there's CO dark gas, and one of the alternative tracers you mentioned was both either C plus or
neutral carbon.
Or neutral carbon. And I was wondering if you could explain why those are good tracers and if there's differences between the two.
So basically, I want to go back to that nice cartoon because essentially, if we look at this, actually this one doesn't show an easy neutral carbon later, but in theory, right, as you go into this cloud, you have mostly C plus. Before you get to CO, there's expected to be some part of that is neutral carbon. There's some transition to neutral carbon before carbon monoxide. Although, to be honest, we don't have like a huge number of constraints on low metallicity C1, I would say. So I think, there may be more of a clumpy structure that means it's not quite in such distinct layers. But at any rate, this should be something that's associated with the CO dark H2. It will be within the CO dark H2 region, essentially. So that could be a useful tracer, and it's not optically thick like CO. There's other, there's some potential plus sides for C1, but so far I don't think there's clear evidence that it's going to behave that much cleaner than CO. I don't know. Anyone want to debate that point? So it also depends on metallicity, the predictions for alpha C1 versus metallicity. So It's another interesting tool in this attempt to really isolate how much of this CO dark H2 there is. Did Jerome have a response about C1, or you had a different question? A related question?
Shall we go to the
Okay.
question first and then let's come back?
I just wanted to check that I understood when you're talking about using young stars as traces of metallicity, it's like you assuming that the gas around the star is similar to the gas, well, the metallicity of the gas around the star is similar to the metallicity of the star. Is that correct?
Exactly. So if you can find stars that are young, they should be quite representative of the gas they formed out of.
Okay. I just wanted to ask, because we spoke about like stellar migration earlier this week or last week, and I was wondering if that is a caveat to this method, or if like this, I guess the time scales or the physical scales kind of mitigate that.
Yeah. So if you're choosing, if your definition of young is, you know, something that could move significantly away from where it was born, then you would have to worry about that. But I think the point people are making is that if you choose a star, for instance, that has a lifetime that is short enough, then it can't have gotten very far away from wherever it was born. So that gas should still be kind of it should still be representative of that gas. But of course, that's, you know, there's the worry you're bringing up, I think, is not unwarranted, because you can't really do this for O stars. I think O stars, the atmospheres are not properly, you can't like have the proper absorption lines to make these measurements. So you are doing this with B stars. And B stars, you know, some of them can have relatively long lifetimes, 100 million years, but hopefully that's still, you know, that's a lot better than 4.5 billion years, which is the sun. So that's the hope.
Thank you.
Mm-hmm.
The roughly the time scale of migration is 1 kiloparsec per giga-year. That's the very rough order. So young stars should be fine.
So first about carbon, I think there will be a multi-beam mounted on C4 prime on charters.
Cool.
So the resolution won't be great, but at least you will have the amount of flux coming from. So, but on this related questions, did anybody try to see H2 at 2 microns?
Vibrational excited.
Yes,
H2.
exactly. So it would be warm H2, but we would expect it to be much more extended than the CO clubs, for instance. And related question again, another mechanisms to measure the amount of molecular hydrogen is to look at the gamma ray. I don't remember the mechanisms, but there is a mechanism of emission of gamma rays, cosmic rays probably eating the and so has it been done? Sorry.
So gamma rays, I think you can do to some degree in the Magellanic Clouds. It's not quite as clean as in the Milky Way, where you have, you know, really high signal to noise. But I think people have measured, does anyone know for sure? I think people have measured dark gas fractions using gamma rays in the Magellanic Clouds, but I don't remember exactly. Other than the Magellanic Clouds, you're kind of out of luck. So that is really good in the Milky Way and kind of the very nearby things, but that's about it. And what was the other question you had about H2 vibrational emission as a tracer of H2? So I think there is actually a lot of promise, not just for vibrational emission, but rotational emission from H2, extrapolated very aggressively to temperatures that are cooler than what actually excites the rotational emission as a possibility to trace the gas. I should have put a slide about that in there, but if you have a really nice rotational diagram of H2, you can model it with a distribution of temperatures and just extend that distribution, like some assumption that it's power law, for instance, down to temperatures that you don't trace with the actual H2. And it does a reasonable job in some cases. And we're about to have a lot of H2 information, rotational and vibrational, from spectroscopy on JWST. So I think there's going to be a lot to learn there.
Yes, but on GWST, it will be only very limited in field of view, right?
So it will be limited in the field of view for the rotational lines, but the vibrational line has a nice narrowband filter that you could potentially use. But I think it's going to be pretty tough to take the vibrational emission of only one tracer and turn that into any useful gas mass, because it's excited sometimes by shocks, sometimes by FUV pumping, sometimes by, like, whatever. With just one thing, I don't know how easy that's going to be. But we'll try everything, right? Might as well give it a shot. It is H2. That's nice. Yeah.
Yeah, thank you very much for the talk. And how the question is answered by the Tanita one. And I need to ask you one thing, that different H2 regions have different stellar populations. Like a few H2 regions have, like, let's say there are H2 regions which have only single, like powered by a single star. Some of them are powered by a bunch of O and B stars. Some of them are by A, G, K, different kind of stars. So how are we gonna determine about the dust depletion rate in there? Like, what is the content of the dust there, and on what basis will define the dust depletion model?
Okay, so there's a lot of things.
I'm sorry.
When you say power in H2 region, G, K, whatever, A star is not going to do anything.
Yes.
So O and B stars only, B stars barely, right? Like O stars pretty much. So I think you're worried a lot about the dust depletion still in H2 regions for your oxygen-based metallicity tracer. Is that?
Kind of, yeah.
Yeah. So what I would say, there's a paper, I can't remember the citation off the top of my head, but I'll find it for you, where they have looked at, Milky Way H2 regions, some SMC and LMC H2 regions, and done their best that they could on, stellar abundances compared to ionized gas abundances to work out what that factor is, that, tiny bit of oxygen that's not in the gas phase. And I think it's like 0.1 dex or less.
Okay.
So it's a small correction. It's not going to necessarily break
Yeah.
anything.
Yeah, I think.
But it's just good to know that it's still there, right? There is still dust in H2 regions. And, if depending on what you're doing, you may have to be that careful.
Thank you.
Okay, any more questions? All right. Was there? I can manage.
Hi, thanks. Great talk. I am at the slide where you discussed the CO dark H2 and the clumpiness connected to it. So I'm a bit confused here. When you this clumpiness, the scale of this clumpiness is on the scale of molecular clouds, or are you talking about the galactic scales?
I think this is quite small scales, but so basically they have a distribution of densities and clumpiness, I think, within the setup for this model, which includes predicting a lot of different lines. And yeah, I believe that the setup is a distribution of densities. This is a pretty new paper, and I gotta admit, I'm not 100% sure I understood all of it. So we do have co-authors, though, in the audience, I believe. Are you a co-author? Do you want to answer that question? No. Okay. Someone else must have read it in detail. Yeah. Do you have an answer to that question? Mm-hmm. Yeah. So we should figure out who's in charge of that model grid project and maybe get you some more answers there. Yeah.
So whatever you said about clumpiness and metallicity, that applies to galactic regions as well as extragalactic regions.
Yeah,
That's what I
so I
understood.
mean, it applies to star forming regions like, you know, the ISM in general. There's, I mean, things are for sure clumpy. And,
Yes.
you know, this is a particular way to parameterize that clumpiness. And their results suggest that it does matter in terms of like how much of the H2 becomes CO dark and how it's represented by C+. So, yeah.
Thanks.
Go
Hey.
ahead.
Yeah, just wondering if there's a physical motivation behind defining the power fraction Q as lesser than 10 to the 3 per cubic centimeter. Is that motivated because of the number density in the ISM, or is it?
So I think that the answer there is probably you need something, and if you go too much bigger, then it starts to become a little less obvious where you draw a line between a grain and a paw. So at some point when they're big enough, they start acting like dust grains more than molecules. And I think probably, but you know, I'm not 100% sure of this answer. Probably it's because 10 to the 3 is something where it's still kind of in that molecule mostly behavior, and it's like far enough away from getting too messy that that's convenient.
Okay.
You make some choice like this in your models.
So one of the reasons too is that when you get very large molecules, they fluctuate. They stop fluctuating at high enough temperature to exhibit those aromatic features. So even if you have a pH larger than 10 to the 3, you are not going to see much emission in the mid-IR.
Yeah. No worries. Thanks, Frederick.
Okay, I don't see any more hands. I do see them. Okay.
I was just waiting. So we see that at low metallicity, paths tend to be more neutral versus.
At least in the SMC.
Okay. Somebody, I can't remember, came to STSCI and told us that neutral paths were more robust against being zapped by radiation fields than ionized paths. Is that correct? And could that explain that trend?
So I think that's probably true. Like one way you can destroy them most likely is multiple ionizations. So they're neutral, they're further away from that state where they could be, you know, the next photon that comes along is the one that does the trick. But it's also the case that they're smaller in the SMC. And in general, people have argued that smaller is more fragile. So I don't think it's clear which one of those wins in that case. And it actually, I mean, the other thing I think is true is that when we see the diffuse ISM, they're actually okay. The places they're destroyed are H2 regions. And so I'm not totally sure if them being, you know, their state of size or charge in the diffuse ISM maybe has that direct of an impact on how rapidly they're destroyed, because the destruction seems to be mainly related to being in ionized gas. I don't know. What's that? Maybe, yeah. There is some evidence that like in BCDs and like starbursty galaxies, the band ratios go back away from being smaller to maybe being even larger. Maybe that's you've eaten away at the small ones, and so you're left with just a tiny bit of pause and they're larger. But this is something your program should answer for us, like imminently. So I think that, you know, it'll be really interesting to know the answer to that.
Okay. I don't see any. So let's thank Karin again for her wonderful talk today.